have started the recording, and today what we'll mostly do the time dependent perturbation theory, fast order perturbation theory, and so we will try to understand that how this spectroscopy is really happening. Okay, so I think you have gone through the lectures, right? And did you that's what we will quickly try to discuss quickly, because we will not derive most of the things. We will do quickly. So is my voice clear right now?
Yeah.
Try to plug it here. Okay. So we'll discuss a two-level system. I'll write it here. Two-level system. So when you gone through this chapter or this perturbation theory, did you have any specific problem or specific queries? Do you have any specific queries? So I will try to stretch upon that part maybe. Do you have any specific queries on this part?
No, not the perturbation, but after it's
Perturb means that two-level theory,
the
or
lectures are.
that lasing thing you had some doubt maybe. Which part can you specify?
Yeah, there's this concept of line width.
Yeah, natural line thing.
Yeah, natural line width that I was not able to understand.
Okay.
And then there are one, two more doubts.
Okay, when
Yes.
I will go there, we will discuss that. Okay, okay. So, so to start with, as you know, for a two-level system, we are saying that most of our molecule, suppose before the perturbation, means before the light is hitting, all the molecules in psi L, and suppose our main system will be given as psi is a perturbation linear combination. So when I am speaking, can you hear me, or do I have to speak this? Okay.
No, now I can hear you.
Okay. So it is an linear combination of these two states, as you already read, psi m. And can you tell me? So this is a perturbation theory, right? First order perturbation theory. So which means, so the perturbation will stay for very small time. Perturbation is small and will stay for very short time, or else it won't be, means we can't, it is an approximation method, as you know that perturbation theory is an approximation method. So it has to be very short time and small. So the perturbation is actually suppose this is our Hamiltonian, so perturbation will be, so whatever was earlier, so this is the zeroth order, means the normal Hamiltonian, and another perturbation part will come, which is actually nothing but mu, suppose mu dipole moment of your molecule and electric field. So first we will discuss with only one dimension, that is mu x direction, and electric field interaction with this electric field. So this is just your perturbation, and Ex is also given as, I think, Ex naught. It is actually should Ex naught should not be in this bracket, but yeah. So and cosine of, I think, 2 pi nu t. So we will not derive all the things. I will just go through all the things quickly. So just after the perturbation, means just we are opening with giving it some light. So at that moment, when t tends to 0, Cl is 1, right, and Cm is 0. Now after the perturbation, with time, what will happen? Cl will be less than 1 and Cm will try to grow, right? Cm will be greater than 0, not exactly it will, and if the perturbation was for too many high times, then it will be almost Cl will be equals to Cm. Cl and Cm are the coefficient, right? And their square will give us the probability. Now I will just taking a cue from my notes. I will just write the Schrodinger equation, and so you know the time dependent Schrodinger equation TDAC is in a quickly. So if it is the form, H psi will give you minus H cross by I d psi by dt, where this is x and time and this is also x and time. So the form here will be, it is like, and do not forget to put the hat on the Hamiltonian. So this is an operator. So it will be something like H1, and it will be operating on this whole psi, right? So this psi is, I will write it here, CL, capital psi. Capital psi means it is an function of both time and space. So Cm, capital psi m, it will give you similarly minus H cross by I del by del t, same thing, Cm psi l, sorry, Cl, right? Cl psi l, Cm psi m. Actually from here we will try to get what is dCm by dt. So so all the derivation was there in the lecture, so I will quickly write the thing what I will get dCm by dt. That is the, that how the this coefficient is changing with time, right? That is most important thing that will come, that is minus I by h, what you will get, I by h. So now see, I am writing not the capital psi, just a psi. So this is actually the only the space dependent part, not the time dependent part. Here we are keeping it outside, exponential minus I Em, acha, it will be plus Em minus En t by, I think, h. So do you understand why we have taken plus Em and not minus Em? Because in the bracket notation, this psi m in this side, this is called bra and this is called k. So this means actually I will just quickly write. So this actually means psi m star. I hope you know this. L and d tau will be a volume element. So actually this psi m star is there. So the in the time depend. So actually it was something like. So earlier it was both in spatial term and as well as in time dependent part. So the spatial part remained unchanged because there was not really any imaginary term, but in the time dependent part there was this I was there, right? So that I, instead of minus Em t by each cut, actually the star was there, so complex conjugate of that will give us plus IEM. So that's why it is looking like this. So this is actually what you get the dCm dt. And what you will do next, that you will put this this H1 was there, so that is minus mu x Ex naught. This cos term will be actually actually this is, I think I am writing.
There's two twice of E naught, EX naught.
Yes, you're correct. 2x naught, right? 2x naught. This is not only.
Yeah.
This is 2x naught. Okay. So this 2x naught and 2.5 will be cutted, and I think you will only have. I'll check. Yeah, you will only have some exponential term, right? That exponential Can you tell me what are the exponential term was there? 2 pi I 2 pi nu t, and I think plus exponential minus I 2 pi nu t, right? Something like this. And this will be minus mu x ex naught exponential. Actually we'll, to keep it in the same dimension, so we'll multiply the numerator by h, and we'll divide it by denominator, and we'll take on h nu. Similarly here h, so it will give us actually exponential I, and I will take this 2 pi in the denominator, so it will be something like h cross, right? H nu t plus exponential minus I h nu t by h cross. So this actually will put here in this place, this perturbation, and we'll get something in terms of dCm by dt. We'll see what we are getting. So what we will get, I will again check my notes because it is a complex term. What is going to come? Okay, it's really a very long term. So this mu x is a space dependent part, right? As we have already seen in the first few weeks of lecture, that mu x is an a spatial dependent part. So mu x not something will come, right? So when derivation of that selection rule we have seen, so the mu x actually is mu x not into some cos term or cos phi sin something. So that will actually stay inside the integration, and ex naught is actually will be act like a constant. So you will get something like psi m mu x psi l, and what else? The rest of the things is, I think, this time dependent part will again come outside, right? Because we can add these things here. So how? Here I have made one miss. Exponential term is there. So exponential. So there will be two exponential term. One will be I em minus el plus h nu common t by h cut, and one will be exponential. So when Sir has derived that, did you try it yourself? Did you derive it by yourself? At least by looking at the lectures, because else it will be very difficult to understand what is happening. Actually, when I was looking at the lectures, I was also trying to derive, and it was actually very hard. Did you find it hard or easy?
Well, it was actually really hard. I'm very bad at maths, so.
Oh yeah, you told me that you didn't. And it would have been then much more harder than. But integration and derivation you right now you know, right? These things.
Yes, I know, but only simpler, equations, not very hard.
Okay, so I will not jump step here. So dCm by dt will get something like this equation, and from there what we will try to get? Well, we will try to integrate the thing to get the Cm. Cm is again this coefficient, and square of that will give us the probability. Actually, in quantum mechanics, this coefficient square will give us the probability, means how much probable that term is, or what is the contribution of psi m you will get in that overall psi. So we'll try to get the Cm by just integrating them. So I will. Can I copy this? But I don't know. I can't I will just integrate it and just bear with me what I am trying to write. So we'll integrate dCm, okay, cm 0 to cm, you can say integrating 0 to cm. And what else was there? We will take the t to there. So already it is minus I by h cut dx naught. Then there is the spatial dependent term when the dipole moment is there. So this is, we are just dealing with one dimension right now, mu x, because the dipole moment or the electric field, that is isotropic, what was discussed. So you can actually take mu by 3 also. So mu x is equal to mu y by mu 3, but we are doing it right now only one. And then what will come? That big thing, right? That exponential not minus I. Acha. I em minus el plus h mu t by h cross. So I guess here, and then we have something plus exponential I em minus el minus h nu t by h cross, and 0 to time t, integration of that dt. So dcm by dt was there, I am just taking here, and t dt here, and I am just getting an integration of that. So what we will create from here? So it will be cm, right? From here cm minus 0, that is there, and what we will get here? I h cross ex naught. So these are all will be acting as a variant. And here I think you might have see Sarah said that some Greville's book, so what they have done, some minus sign and something, so it might have confused him. So what actually we are going to get, I am writing here, then I will discuss that what happened. Okay, so what will happen now? Yeah, I have made one mistake. See, so here it was minus mu x, right? And it was minus already here. So actually it is plus. Okay, so it is actually plus right now. Now what will happen if we integrate the exponential term? First we will get something in the denominator now. So that is what we will get, I by h cross em minus el plus h nu. T is the variable here, so the integration will again give us exponential I, same thing, em minus el plus h nu by h cross. Now at t equals to time t, it will t, and at t equals to 0, it will give us exponential of 0, that is 1, right? So we have already done the integration here. So did you understand this step, what I have done? em minus el t. Avantika,
Yes.
did you understand that step? Why this is minus 1, or how this minus 1 came?
No, actually.
Okay, I will tell you. So the thing is, so we are doing the integration of this, okay? So integration of this means, suppose integration of some exponential time, let me write it in, suppose this I, em, this or each card, this is all, suppose a, one constant, and t dt, suppose we are doing this 0 to t integration of this. So this will actually give us, the formula is 1 by a, okay, the constant term 1 by a, and then we will integrate means the exponential at will be exponential at, okay, and the limit is t to 0, right? So it will give us 1 by a, and exponential at t equals to t, it will be exponential at, and at t equals to 0 it is exponential 0, right? And e to the power 0 is nothing but 1. That's what is happening here also. Okay, so I have taken this, all this thing constant as a here. Did you understand how this minus 1 came for the both the part?
Yeah.
Okay. So this will actually then lead us to Cm being I by h is already there in the denominator, so we can cut it. So Ex naught is there. Then this transition moment integral part is there, right? This is also known as transition moment integral. This part dAmi. So this is what we were discussing in the previous lectures. Now exponential. Well, so I will take 1 minus something, minus of this. So what Sir has used the convention from the Greville's book. So in the Greville's book this minus sign is not there, but that is not really an important thing, that I think you have already understood, because we will take Cm square, right? So that doesn't really matter. Yeah, plus h nu d by h. So there are a lot of lengthy things here, so don't worry about that. Em minus En plus h plus 1 minus exponential again I by Em minus En minus h. So this actually is going to come as very handy formula, very important, not handy. Em minus En minus h. This is what I was doing, a different thing. Okay. This is not part of it. So what you are going to actually see now, one thing will come. See, the Cm, the value of Cm will blow up when, so blow up means, see, if the denominator is less, right, then the overall fraction is very high, the value is very high if this is very less, right? Am I making sense what I am trying to say?
Yes.
Okay.
Yes. Yes.
And each cart is also very small, right? Each cart, because each is already 6.6 into 10 to the power minus 34, right? And it is already there in the denominator. So suppose how much this exponential term is high, right? This is very high. So now suppose what I am trying to say. So now when this will close to 0, means the denominator, what I am trying to say, so the things will again blow up. So Cm will be very, very high, and when Cm will be high, that means transition is taking place, right? Because at t equals to t tends to 0, there is only Cl. The Cm was 0. Cm is the coefficient of the that the higher energy state, right? And Cl is the lowest one. Now what I am trying to say, now when this denominator is very small, this one, suppose when these two denominators is 0, close to 0, suppose what does mean? El is minus H nu, that actually means EL minus EM is equal to H nu, right? Because H nu is a positive quantity. And another, from here, the second part you will get EM minus EL to be H nu. So this is when, suppose when EM minus EL will be H nu, so this will be almost 0, right? This is 0 denominator. Then CM will be very high. I hope you are getting my point, right? And this is actually known as Bohr resonance condition. Okay. A resonance means this energy is equals to this energy. Means this H nu we are giving, and this is the difference between two states, right? EL and EM. L means the starting one, means, or the you can say initial. M is the final. Okay, so when EL minus EM is H nu, that means the transition. So there are two things. So we have started our discussion with L being the EL being small, right, and EM being high. So this is M. So this is where we have started. So it will go to L to M, right? This does mean, right? So this is actually an absorption process, which is this part EM minus EL is equals to A. This is coming from my absorption, and this is actually coming from. So this is L and M. Because now L is always our initial step, right? L to M transition. Now if EL is higher than EM, that means L is the higher energy level. Now that means this is an emission process. But we have to understand this is an induced emission and this is an induced absorption. What does that mean by induced? Means we are giving some photon and then it is happening. And similarly for this emission process also, this is an induced emission process, and this is happening at Bohr resonance condition. Means at Bohr resonance condition, this denominator is very small, and that is why CM is very high. So did you get this part, or should I repeat?
No, I got it.
You got it. Okay, very good. So now next what we will discuss, that what is actually the CM for absorption, and this is for CM for induce, and then we will go to the CM stuff. Okay. So only for absorption process, so we will not discuss. See, absorption is always induced, so I should not write absorption bracket induced, but emission could be induced and spontaneous, that I think you have gone through. But let us talk about absorption right now. Okay, so what we have got for CM, we have got something like Ex naught transition moment integral psi L, then what we got, exponential. Acha, we got 1 minus exponential, right? Yeah, 1 minus exponential I EM minus EL minus H nu, minus for absorption E by H cut, and at the denominator we have EM minus EL minus H nu. Okay, so this is what we have for absorption. I think we can take one minus sign or not. We got a minus, I guess. Yeah, we got a minus here, as you can see here. We got a minus here for both the things. So let us go with this. And what we will try to do, we will take some assumptions here, that will take a constant, that is A equals to pi by H, not H cut, pi by H, EM minus EL minus H nu. This is the constant term into time t. So A is not actually a constant right now because time t is there. Okay, so what we are trying to do, we will try to simplify this. So what else we will get from here? We will get that em minus el minus h nu will be h a by pi t. Okay, so let us take now what is the value of Cm, that is minus Ex naught. Again the transition moment integral, I think we can write it in a different fashion. After this 1 minus exponential, now this term has less I Em, this means this is already there, T is there and H cut is there, so let me write it once, HA by pi T multiply by T by H cross, and in denominator we have got HA by pi T. Okay, so we'll have minus pi T Ex naught, this psi m mu x psi l, and 1 minus exponential I h gone, a will be there, t is gone, I think, am I making any mistake? Yes, no. So what else is
2
there?
pi.
2 pi will come. Acha, this h cross again means h into 2 pi. So pi cancel, t cancel, 2 is remain, right? 2 ai. Yeah, very good. 2 h is also cancelled. So what remains? ai and 2. Okay, I guess so. And in denominator pi t we have taken here, so we only have ha. Now the most important step. Now see, we need to get the probability or the contribution, or let me write it here once, contribution of capital psi am to psi, capital psi, that is the linear combination, right, is psi m square, actually psi m mod square, that is actually not psi m square, but in quantum mechanics we actually write it Cm star by Cm. So you have read quantum mechanics, right? The basic of quantum mechanics, did you read them in any courses?
Yes.
Okay, so there you know that this is what is the Cm star, right? This is a complex conjugate of this Cm, and this is the only Cm. So we will take that. Anyway, you can see minus will again be plus, right? So the sign didn't really matter. What actually will matter, we will see. So pi square, t square, now ex naught square, now this probability, this transition moment integral, that square, and what else is there? And now there will be something different, I guess. What is there? And let me take the h square also here, and what is else there? 1 minus exponential, right? Acha, so this will become 1 minus, so first term is coming from Cm star, right? So Cm star will be, so this is Cm, so this is Cm, right? Cm star, I will not write the other terms, I will write it like that, and here it will be 1 minus exponential, same 1 minus exponential, but here 2 ia, right? Because the complex conjugate, because the imaginary term is here. I have not written anything else, everything same, just a minus inside. So it is 1 minus exponential of 2 ia, right? Actually the first is minus 2 ia multiply by 1 minus exponential plus 2 ia. and then divided by a square. What this will actually going to give us, let us check. Pi square t square dx naught square. Actually from this cm square we will get all the other things what sir was discussing. So I will take it in a what sir has written later, psi x l lm, right? So this is also the same thing, right? So I'll just short it. 1, so what we are getting from here, 1 minus another term will get minus exponential of minus 2ia, then minus of exponential 2ia, and a multiplication of this, right? Exponential minus 2ia, and minus minus it will be plus 2ia plus 2ia, which will give us 0, exponential 0 again, and which is actually 1, right? So from here we will get what we will get. We will get pi square t square dx naught square h square. So I told you that I will not do much math, but I am doing. So this 2 minus, now exponential of minus 2ia. So that is actually what is that? But that is cos 2a minus I sin 2a, right? You know this from I think de Moivre's theorem or something like that, right? Or Euler's theorem, I guess. I always interchange the name, I don't remember. Anyway, so and we also, I have taken the minus common, so this is also plus, exponential of plus 2ia, so that will give us cos 2a and plus I sin 2a now. 2a. And I have taken this already 1, 1, 2, so I am not writing it again, a square. So this will cut, this will cut. Now we will get 2 cos, we have 2 cos 2a, so I can write 2 pi square t square dx naught square by h square. I hope I understand, you can't see that part. Me too. Now 1 minus cos 2a by a square, so that is actually nothing but 2 sin square a, right? So 4 pi square t square dx naught square by h square into sin square a by a square. That is actually your cm square, right? So this is what we are trying to get. And from here the concept of light broadening will come. So just see, So I'll just go to the next page and I have missed one part, I guess. Yes, I have missed the transition moment integral square. I'll just write it nicely here. M square is equal to 4 pi square t square h square dx naught square. I'll write this term again, mu a, and sin square a by a square. So this is your space dependent part, right? Space, and this is coming from your time dependent. Now, so these are your 2 levels for absorption, right, or emission, you can say. This is L and M. Okay. Now what Sir is saying, or what is there in the Heisenberg uncertainty principle, that there is some uncertainty in delta energy and delta time. I think that is equals to h cross by something like that. Okay, means there are some uncertainty. So now this is the L state, this is the M state. Now this is the ground state. Okay, so what do you think? What is the lifetime of this state? Lifetime of L. Avantika, can you tell me what is the lifetime of this ground state? And it will stay here for forever, right?
Yes.
So the lifetime is, so you were saying something?
It will be infinity. I mean, it's ground state, so
Yeah, it will be infinity. But as you can understand, so here the if the lifetime is tau for the excited state, so there is an probability that there is some uncertainty around tau, right, or less than tau. So suppose tau is the lifetime of the excited state, that EM. Now there is some uncertainty here. So as there is some uncertainty in time, so there will be some uncertainty in the energy as well as of the excited state. So that's why EM could be here, your excited state could be here, or could be like this. Okay, so that's why we will see when you excite your sample, it can go either here or here or here. Now it can emit from any of those states and you will get some line broadening. So this is known as natural line broadening. Okay, so do you understand right now what I am trying to say, or do you have still some problem? You can tell me. So there are two ways of thinking this. Another is sin square A by A square, right? How this will look like? Do you know how sin A by A looks like? So this function actually looks like, sin A by A. That's why some negative part is there, and actually you will see there we have to get a limit A tends to 0, then it will be 1. So at A equals to 0, here there was some discontinuity, but it is a removable discontinuity. Sin A by A look like this. So how does sin square A by A square will look like? It will actually look like, so there will be no negative part, right? And now it will look like something like this, and this is higher than this. I hope you are getting my point what I am trying to say. So this is A, right? And this is A equals to 0. So what from the equation what we are getting that here, so we actually this A, you will see this, what is this A? We have shorted right? A is pi by H EM minus EL minus H nu, and there is some T term. So the nu is there, right? Nu is the energy or frequency. This is a dimension of energy also, right? That means in time, so there is some line broadening, means not only from this nu you are getting from, suppose this is nu 0, and you are getting some from here and from here also. So actually, and that's why, so this is your probability right? Probability of transition, Cm square, transition. But as this is not actually a single line thing, this is actually a broadened thing like that. That's why you need another thing that is known as probability of transition integrated over the band. this is not your spectra. Your spectra will actually look like this, and this is for only one nu. Don't think that in emission spectra we get something like this broad spectra from 400 to 500 or 600. We get something like this. This is not that. This is only for one wavelength. Only one wavelength. So you should have got only one spectra. 450 you should have got one spectra, but your line, there is some line width. So that is what we are discussing. Okay. So this is not this broad spectra of your emission, but what we are trying to say, suppose at 400 you are getting 400 plus minus something. So that plus minus something is very few, but it is not actually a line, but broadened line broadening. That is what we are calling a natural line broadening. Okay, and this whole big peak broadening is a different thing. You can read it from Van Oil. Okay, in Van Oil it is there. Okay, did you understand this part? What I am trying to say? What is natural line broadening? Or do you still have some doubt? You can ask me.
Yes, you said actually uncertainty in energy, right?
Yes.
But the energy levels are defined.
That is the thing, na. So energy levels are it is defined in the macroscopic thing, but when you see from a quantum level, so if there is some uncertainty in time, so there will be some uncertainty in energy. This is that Heisenberg principle. So this is a universal phenomenon. Okay, so there will be some uncertainty in energy of the excited state, but there is no not means you can say no uncertainty in the excited energy of the ground state, because the lifetime is already infinity, right?
Okay.
Okay, so that's why when you are getting some uncertainty in the energy, that is why you are getting this broadened line. You should have got something around the nu zero. Okay, but now you are getting from here or here, something like that. Okay, so that is why you are getting a broad peak instead of a line. That is what called as known as a line broadening, and that is also evident from your equation, probability of transition. This thing, sin square a by a square will give you this line broadening. So this broadening and this broadening actually is the almost the same thing what I am trying to describe. And as this thing is coming, so you need to for probability to get the probability of transition, you need to integrate all over the band. So what that does mean is PL to M, that transition is now integrated over Cm star by dA, right? Or d nu, sorry, because here we are taking as nu. So nu means we have already assumed dA is equal to this. So what is our d nu then? dA is pi d by h. Now dEm by d nu is that 0 minus 0 minus h will come up and d nu. Okay, so these are constant here. Em minus here now constant. So these will give us dA is equal to minus pi h cross d nu. Can we make it simpler? I guess so. Pi will cancel. What will be there? Am I making any mistake? Yeah, it was not h cross, it was h. H got minus pi t d. So Sayer has taken ignored this minus sign. I also didn't understand why did he take that, but let us do like what he has done. pi square t square e square ex naught square. Now I will take this L to M square, and what we are getting now, sine square by A. So there will be integration, right? So what is the integration look like? So if I change it to d mu to dA, it will be Cm star Cm, and then d mu is minus dA by pi t or something like that, right? So pi t will come here, and it will be dA by pi t here, and now the integration limits will change. The integration limit will be minus infinity to plus infinity. If you see this image right now, so we are taking from minus infinity to plus infinity for A, right? So minus infinity plus infinity, and what is the sine square A by A square dA. So this is PLM. Okay. This is actually going to give you PLM, and this is actually is known in the literature that minus in, so we cannot really do all the mathematics. So this is actually given in literature that this is actually pi. Okay, this is the actually definition of pi. Okay, so we will take it here for pi t by A square ex naught square, and pi square will come here, right? And mu Lm square. Okay, and another term, that energy density rho nu is introduced now. Energy density, which is given by Ex naught square by 2 pi, and that will be 8 pi square. What is going to give us? Let me check. What will get them? Ex square 8
Pi cube.
pi cube, right? Pi cube t by h square. Now this is rho nu, and your mu Lm, that is your transition moment integral square, and this is your that. And now if you take a rate equation from this, or if you take, I'll go to the next page, the transition from PL to M and its dependence over time, or how it is changing with time. If you take that, so what will get? 8 am I making? Yeah, 8 pi cube by h square, right? Then rho nu, and that psi m mu x or psi m its square, right? And I can now take, as this is isotropic case, dPLM L to M dt. You understand, this t is gone because I am derivative with respect to dt. We are getting a derivation of that, derivative of that. So 8 pi cube by a square rho nu, and same I guess I am. Why I am writing this? is actually known as Fermi's golden rule. So actually, see, in net or gate, this much thing is not really important, okay, to be honest. But suppose to understand the subject, why the spectroscopy is going on, this is required for that purpose. For net gate, you will not be asked. But suppose you are going for any interview and you are working on suppose physical chemistry or spectroscopy something. So their favorite question is this: what is Fermi's golden rule? Okay. So you don't have to remember this thing. So what you have to say that this is actually give us an idea about the rate of the transition. So this is rate of the transition, right? Rate of transition, you can say, right, is dependent on rho nu. So that is coming from the radiation, right? So that is a property of the radiation. And psi m, this TMI, transition moment integral, is coming from your matter, right? What we are discussing right now, we are discussing semi-classical treatment, right? Meant on interaction between radiation and matter. So this is giving you a kinetic equation where if we are discussing about radiation and matter, so that is why it is known as a golden rule. Means it is giving you the feel of chemistry, right? Suppose A plus B is giving you C, then the rate is formation of C is what? Is the rate constant into depends on A, B, not to the power, suppose M and N. We don't know the order, right? So that is something different thing, right? What is that thing is known as the order of the reaction as versus molecular, what is that called? I forgot, I'm very sorry. Do you remember that what is that is called? The rate thing, this is M plus N is the order of the reaction, and some molecule, that thing is called
Molecularity.
molecularity, right? I don't remember that. Yeah. So that is not always the same, right? So other than that, what you can understand that you are getting a rate of transition, and two main involved part is your radiation and your matter. So this is indeed a beautiful equation. That is why it is known as a Fermi's golden rule. So this is actually giving a kinetic equation. Did you understand till this part?
Yes.
Okay, very good. So we will not discuss much more because I think your Einstein formula you got it correctly, right? Or do you have some doubt there? So I will just yes.
I got it. And the coefficient.
Okay, I will just write the thing Einstein treatment. I will just give you the thing where we'll get that BLM, that is your Einstein coefficient of the induced absorption, is equals to your opposite thing, right? M and N. This is M and this is N. So that is equals to B, and your spontaneous Einstein coefficient of spontaneous emission by this B is actually nothing but 8 by H nu cube by C cube. So Sir has already shown that this part will have something 10 to the power minus 56 something. Okay, and let us go to our old slide. So this is a very old slide of ours, right? This. So as you can see, when we are going from radio to microwave, infrared, visible, ultraviolet region. So what is actually happening? Our lambda is getting small, but as lambda is getting small, our frequency and energy is getting increased, right? So the frequency of ultraviolet region is higher than the microwave region. So that's why I have kept this slide, so that we may have to go here and there. So for a microwave case, okay, for a microwave case, when, so that is, what did we saw there? I forgot the values. I'll just check the values of the frequencies. So the frequency was 10 to the power 8 in case of microwaves, and in 10 to the power 16, right? Almost double, not double, almost double the order, right? So for microwave it is almost 10 to the power 8 hertz frequency, and UV is 10 to the power 16 hertz, much more energy in case of UG. So as you can see, your spontaneous emission constants. So this is your for spontaneous emission, right? From there you will get that your one thing, that if you have some B, if your B is non-zero, means if there is some absorption, you will get some emission, that is spontaneous emission, right? Emission you should get, but now that also depends that what is the wave, what is the induced, means what is the light we are using to excite the sample, okay, something like that. So when we are using a microwave thing, then you can see your spontaneous emission will be very less, right? Because 10 to the power minus 56 into 10 to the power minus 24 plus 24. So your A is right now is spontaneous emission for this is 10 to the power almost minus how much? 2 and 32, right? I'm just writing the order. So for this is for microwave, and for UV you will get 10 to the power minus 56 into 10 to the power plus 16 into 3, that is 48. So it is very less, right? Very high. So for your UV excitation, you will see your UV region, you will see your spontaneous emission is very high. So as your spontaneous emission will be high, then you will get, if this is high, you are getting less stimulated emission, okay. So if you want to make a laser, what is the full form of laser? Can you tell me, Avandika? What is the full form?
Oh, well, I forgot actually.
Okay.
Laser.
Okay. Light amplification by spontaneous
Light.
emission of radiation, right?
Ready.
Sorry, not spontaneous. It is stimulated, right? It is stimulated. So in case of laser, it is stimulated. So if you are getting less stimulated emission in case of, see, the UV region, but in microwave you are getting a higher stimulated emission, less spontaneous emission, right? So then a laser in the microwave region preparation is more easier than the UV region. So this kind of question can come in the NPTEL is all about. So if you are going to give an final exam, so all the things will be actually MCQ or MSQ type of question. There is not really any this kind of derivation or this kind of question. But suppose you took this course for also help in your courses in classes, universities. So there, this is a very common question that from Einstein treatment. So first they will tell you to write the Einstein treatment, and then why the this kind of laser in microwave region we can prepare, but UV region is hard to prepare, something like that. This kind of question will come. I hope you understand, right? Why we are getting something like that. Okay. So another thing is that your BLM, that is your coefficient, Einstein coefficient for induced absorption, that is also equals to 8 pi square, that 3h square, your transition moment integral square. Why I am writing this? So this has come from your, so this was there in your Fermi's golden rule, right? This part actually not this part, this part, not the H nu, rho nu part. Rho nu part is a different kinetic thing will come, right? This is actually your B. Now from here, this is also your B ML, right? What we have established, this is B, and now this is also, you know how your B is. Your B is 8 pi cube, or no, 8 pi H nu cube by C cube B, right? So these are the relations what sir was saying, I guess. So you also from lecture 20 you have introduced to another time, right? So stylized A, right? This thing you have been, I think, being introduced to in the lecture 20. So did you understand what is that stylized A is? Integrated absorption coefficient. So this is because of the same region that there is some line broadening. Earlier in case of Beard-Lambert's law, we got something minus di by I is equal to nu CL, right? A dl, right? Something like this. Now as it is not a single band, it is something, a line broadening is there. That is why you need to do get something instead of alpha nu, you need something, this integrated absorption coefficient. So that is actually your let me write it here. So when you do that integration over the band, we will get minus di by I equals to stylized A C dl. See, we are yet to do the integration to get epsilon CL, something like that. So you can understand, right, that what is your A is. I will write it in the next page. So minus di by I, that is stylized A CM dl. What are the other forms you already seen? That is minus di by I 8 pi square. So you understand now why sir has taken this 1000 and other things while discussing this part.
Yeah, but actually there was something. There's actually one LM,
Yes.
and he said this is energy removed. I could not understand this
Acha,
part. How is
I will take this. Okay. So I will try to write this again. Acha, let me write this part from the beginning. See. So we already got your probability of transition, right? Rate of probability of transition. So that is your 8 pi square 3h square your that same thing
5Q.
rho mu, right? So now for a now
It's
suppose
5Q.
yes,
It's 5Q, no?
I guess so. I think yeah we are doing one mistake here. Yes, this is 8 pi q. So I have made that mistake here also somewhere. Yes, this should be 8 pi q, right? No? Because here it is 8 pi q. Yes. Okay. So this is 8 pi q. Okay. 8 pi q. This thing, and suppose now there are, so this is for one molecule. So this is what? This is your dPl2m by dt. Okay, this part. Now we are multiplying with, suppose one molecule is getting excited. Now so suppose this is your molar concentration Cm. Okay. So what do you think? How many molecules is there per centimeter inverse? So this means Cm means Cm into Avogadro number of molecules per liter inverse. Liter inverse means same as decimeter cube, not per, decimeter minus 3, and it is same as Cm into Na by 1. So here also we are just playing with the unit. Okay, so molar concentration Cm means this many molecules per liter, that means this many molecules per decimeter cube or per decimeter cube, and this many molecule per centimeter cube. So for this many molecules, so this is the probability of transition. Now Cm into Na into 1000. Okay, and so these are all one photon thing, right? One photon absorption. So if these many molecules are there, so they will absorb total of this into h nu lm so this much energy will be absorbed, right?
Yes.
And the probability with time, and the rate of probability is, you will get if you multiply that with your this function. Okay, so this is your energy and this is a rate term. So your kinetic term, what is there? What is the unit? So probability, there is no unit, but time is there per second, something like that, right? So this is your probability per time, or a rate of probability, right? This part, this round part, what I am showing right here. Yes or not? Do you agree?
Yes. Hmm.
So no. If you understand, then you say. I'll say again. So see.
No, I
Okay.
understand.
So this is part time, right? And this is energy. And how many molecules are there in unit volume? So this is Cm per liter, right? And so at unit cross section, and the length is dl, right? So this will, and at unit cross section. So these are also giving us our volume term. So this much energy per time is getting absorbed per unit cross section. Is this making sense, what I am saying? So what is actually happening when it is passing through the sample? Suppose I naught is falling. Suppose this is a cross section whose length is, suppose this is a cross section whose length is dl, and cross section is, suppose unit cross section, and the whole length is l, obviously. And in this unit cross section, there are this many numbers of molecules So they will absorb this much energy, means the total energy is this, and the probability per time, and per time the probability is multiplied by that. So eventually you are getting energy per time, right? Isn't it so? Energy per time,
Yes.
and that is your intensity. You know this, right? Energy per time.
Ye-
So that is being
Yes.
absorbed per unit cross section. So that is why it is giving like that. So that's why your minus di, that is being intensity being absorbed, is 8 pi cube by 3 a square, and then your this transition moment integral square. So this is not your dipole moment modular square. This is your TMI. Okay, don't forget this. And then your rho nu energy density is there into Cm into Na into 1000 into H nu Lm into dl. See? And this eventually will give you, I think, I is equal to C into rho nu, and so rho nu is I by C. So this is your I by C, right? So you will take this thing di by I. So it will eventually be 8 pi cube 3000 H 1H will cut mu Lm square HC and dl, I guess. Am I taking all the things out? Na, Cm are also there. Na, Cm and dl, right? Okay, so you got it. What happened actually per unit cross section, how much intensity is being absorbed, right? That is what was the main concern with us, right? In Biot-Lambert law or in absorbance, it is falling at I0 and coming out of the cuvette as IT, right? But at a unit cross section we are saying that, right? So unit cross section means the length was dl. Now we are bringing the concept of unit cross section. At unit cross section, this many molecule is there. They will absorb. If the probability is 1, if the probability this was 1, then they would have absorbed this much. But there is some probability, right? This many transition can happen. That is why this probability part is multiplying with this total energy term. This much energy can be absorbed. There is a probability that this much energy can be absorbed, and that is actually your reduced, or what is the absorbed intensity. And ultimately you will get from there, you will, so you have already got earlier, you got alpha nu Cm dl, but now as you know there is a natural line broadening. That's why, sorry, I am writing it in this fashion. Stylized A you will get because there is some line broadening, right? So integrated over the band. Band will give you, so this along the band d nu, this is the frequency Cm dA. So actually you are getting your, what is your A? Stylized A, that is 8 pi cube mu Lm square Na Cm, not Cm will be there, right? Cm and dl are here, and 3000 AC. So I will just this part. Now sir has told you to get a relationship between A, stylized A, capital A, and maybe B. What are the possible relationship? Because you already know this is B, right? Uh, and use it another pen, another color. Where is my another color? This is your B, right? This B. Now you can get a relationship, right, between stylized A and stylized B. Now when you get the B, now you put that formula that A is equal to 8 pi H nu cube by C cube B, right? So from B you replace B here, then you will get a relationship between stylized A and capital A. So that's what I guess sir was trying to say. So did you understand this part? Do you have any doubt here?
No.
So I hope this was helpful. So next, then I am not going to that laser system or the population inversion and those things. That is the week 5 thing, because I guess we have already done too much mathematics, right? And we have only half an hour left. So we'll quickly discuss the assignment problems, and maybe tomorrow. I thought that today I will cover half of the week 5 lecture quickly, but let us not do that. So do you have any doubt from the week 5? Did you gone through the week 5 lecture as well as?
Yeah, I have. Just the last one is, I think sixth one is remaining. I've seen it once, but I have to
Okay.
just
So
fix
okay. So in week 5, actually, I think it is discussed more about that laser 2-level system. Actually, is not possible for population inversion, as population inversion is not means the population of the excited state will not be higher in case of from the ground state. That's why the stimulated emission can't be higher than stimulated absorption. So there will be no net gain. So that's why you will not get any stimulated emission or net stimulated emission. So you will not get the laser system for a 2-level system. I hope you read these things. These are very, I think, simple. But mathematics is, I think, a little tough, or maybe a lengthy, you can say. Not really tough. Means try to solve this by yourself. While sir is saying, means pause the video and try to go for the next step and see if sir is also doing the same. So see, nobody will in most of the cases in this course, at least at the end, if you opt for the exam, you don't have to derive all these things, but you should do this. Suppose Rabi's oscillation, what is that? You should know this thing and what is the effect of that. Anyway, so we will discuss a few of these things in the next class. Let us go to the assignment. So this is the week 4 assignment. We will quickly do this. So you will give me the answer. So question number 1, in semi-classical treatment, let me change the color of my pen here. Okay. So in the semi-classical treatment, the interaction with radiation with matter, the treatment of radiation and matter is respectively. Can you tell me what is the radiation and what actually is the matter? That's what.
radiation is classical and matter is quantum mechanical.
Okay, so this is matter is quantum mechanical and radiation is classical, right? Yeah, correct. Then what is the space-time dependent wave function of a psi x y z t is given, then which one is correct? Can you tell me?
The second one.
Second one. So energy is actually a constant, right? So let me again solve this thing quickly. So this is your time dependent Schrodinger equation. So while I will do that, you can change your answer. This is your capital psi dependent on x and t. This will give you minus a squared by I d by dt.
No, it is fourth one.
This is the first one. So I'll give you another time to change your answer. Okay, that is not also correct. So your time dependent part will come here, and only your. So I'll just only writing x, x y z t, x y z is there. So I am giving you another time to correct your answer. So here only the time dependent part is there because del t. So psi x will come out and del phi t by del t will be there. Now this is almost d, right? Not del. And I have taken the approximation that psi x t is psi of x phi of t. I will now divide both the part by psi of x phi of t, psi of x phi of t, that will lead to what? This is going to 1 by h psi x by psi of x is equal to minus h cut by I 1 by phi of t d by phi of t by dt. Now see, this is only space dependent part, this is only time dependent part, right? So separation of variables have been done. When these two things can be equal? When it is equals to a constant which is neither depend on x or t. This is a constant. Okay, so you will get here that h psi of x is e psi of x. This is your time independent Schrodinger equation what you solve generally. And another thing you will get d phi of dt, d phi of t will give you minus I e dt by h cross. Now we will take a integration, right? Integration will give us ln phi of t is integration over time 0 to t, something like that. Suppose it will give us minus I e t by h cross plus some constant, suppose. Let us not, okay, let us be that one. And now what is your phi of t? Exponential minus I e t by h cut. Okay, plus some constant, that is, so suppose that is not there, constant is not there. So what actually you are getting now? Can you tell me what is your overall psi, capital psi? Suppose now it is x y z t. So it is your psi x y z into phi of t, right? So that is psi of x y z and phi of t. What you got? Some exponential minus I e t by h cross plus some constant. something like that, right? You got it? Now, actually the answer should be C, but I guess there should have been this H cross was there, right? Did you get it? So this is not your time dependent pass, psi is spatial, right? So else it could have been the right answer, but again there is no minus is there. So this is your correct answer, third one. And in these two and fourth option, E is dependent on x, y, z, but actually not. E is actually a constant. Okay, let us go to the next question, question number 3. So question number 3 says a spectroscopic transition in the language of quantum mechanics is, out of these 4, which was in the correct answer? What do you think?
Mixing of states.
Yes. So again I will write the main equation what we were trying, we were solving for this much time. Psi L plus Cl of psi M. So this is actually superposition of states, right? States or mixing of states of psi L and psi M. And now time dependent perturbation used here is of what order of perturbation did we talk about? We write it something like this, right?
First order.
Yes, first order perturbation here is. Now question number 5. For a transition between two states, we obtained this, right? dCm by dt is minus IH by psi m. This should be not H1 psi m exponential of this, right? We have got this, where H is the perturbation correction. Okay, got it. So what do you think? Which are option are the correct options? The wave function depends on space, not time. What do you think? Is it a correct answer?
The integral is over space and not time.
Yes, the integral is over the space only, right? Yeah. So integral depends on space, not time. And acha, you are talking about this integral is over the space and time. And what about this? Here is this, because I have a doubt with this answer. So in the correct option they have written that the wave function depends on space, not time. But so the wave function we are dealing with a capital psi, right? So it depends on time. I think the right answer is C, but they have in the thing they have written as the wave function depends on space, not time. What do you think?
But the time is taken outside, no?
Time is taken, but they are saying not the transition. They are not saying of the transition. They are saying the wave functions. So wave function depends on the space and time, right? But transition here will be integral over space, right? So I have a doubt here. So I if I had the option, I will go with this only one option if I had some doubt, because if this is marked as a wrong answer then I could have lost all the marks. So I would have gone with this only one option. The integral is over the space, not time. What do you think? The wave function depends on both space and time. The integral doesn't. Integral is on the space. So that is what we are correct option we are choosing. But what about the wave function? What do you think? So I will discuss with the TA who is sitting these answers. I will discuss with him and we'll let you know. Okay. Let us go to the next question.
Okay.
So the periodicity of the electric field of light is written in terms of exponential rather than the trigonometric form. So they are talking about this part, this thing, rather than the trigonometric part, right? We are going to the exponential thing, right? So that is the question, that periodicity of the light is written in the exponential rather than the trigonometric form in order to, out of these four questions,
Simplify that question.
actually yes. So these are actually very bad questions, right? Actually bad questions. Anyway, so the question number 7, Bohr resonance condition. This is what we have discussed, right? That EM minus EL is either H nu or EL minus EM is H nu. Is achieved ensuring dCm by dt is 0. I guess not. Is achieved ensuring Cm not is equal to 0? Actually no. Actually it is coming from the time dependent part, right? So that exponential thing what we have discussed. What do you think? That Cm was minus Ex naught psi m ux psi n multiplied by that 1 minus exponential blah blah things tau, right? Something like this, divided by em minus en minus a. Let me write it down only for the absorption, then I could have write only one term. This is E2 in this. So this is coming from the time dependent part, right? Not from the spatial. Okay. So question number 8, phenomena that do not rise directly out of time dependent perturbation theoretical treatment of the problem of interaction with radiation with matter are. So we have already discussed absorption, right? Here you can see. Then induced emission, right? So this is the for where the denominator Em minus En plus H. So this is induced emission and this is for absorption. So tell me which are the things that do not directly arise. So absorption.
Spontaneous.
Yes, spontaneous emission, stimulated emission directly arise. What about other? What is left? Non-radiative processes. Did you read the?
Non-radiative.
Yes, actually when you
Yes.
read the week 5 lecture, it is there, right?
Yes.
Yeah.
Yes.
Again, you are telling me, sir.
I forget. Well, you are teaching me, so indirectly you are.
I am not teaching. We are discussing. This is a discussion session. I am not teaching. Don't. This is a tutorial thing. Okay. So that's what I think. This. Acha, another question is there. Question number 9. Question number 9 is natural line with arises from. What do you think? Natural line with. So this was that sine square a by
Time
s.
dependent.
So space dependent part cut, time dependent part of the wave function, right? Induced dipole moment cut, quadrupole moment cut. This is the right answer. Okay, so these are the question you are already got. So tomorrow on the next week, I hope we will quickly finish week 5. Means what I am trying to do, that I want to do 2 weeks of material at a day, so that we can cope up with that. So maybe next week I will do week 5 and week 6 discuss, and then do the assignment for week 5. So you read week 5 quickly, because I guess you So are you submitting the assignments?
Yeah,
So when is the submission date? Week 5 assignment.
it's tomorrow.
It's tomorrow, so you need to read it by tomorrow and solve it. How many questions are there? Question 8 questions are there. I guess you will do it quickly because I guess all are not mathematical question. So I guess you will solve it, and I guess tomorrow we will do that. Tomorrow means the day after tomorrow. Acha. So let me stop presenting. Okay. Okay then, Avantika, we'll meet the next week then. Thank you for joining. Do you have any other doubts or?
No,
Okay. Okay then, we'll meet.
thank you.
Thank you. And
Have a good evening.
if you find some questions online or in books, please share here, so we can discuss that sample questions as well. Okay. If you find any question from your book regarding the rotational or IR, whatever till we have discussed, you check your books or question paper, net papers. We can discuss.
And do you have Craven's book?
I don't right now. I will check if I have in PDF or any version. I will try to share it with
Okay,
you. Okay.
thank you.